I'm JP Vassar, Cisco Fellow, VP of Engineering. I've been at Cisco for 25 years, and I've been driving ML/AI for about 12 years. What I would like to do today is to walk you through what has been an amazing 12-year journey, innovating on all fronts in many areas, shipping product at scales, closely working with customers, and I will try to do that in less than 20 minutes. The journey started in 2012. Remember, at that time, there was no cloud, almost no ML/AI being used for networking. We started the journey by looking at the first use case of Internet of Things. We had come up with a new routing protocol called Ripple that allowed it to interconnect some smart devices, and we wanted to enhance the routing decision and also be capable of detecting some denial of service attacks. And for that, we started to use machine learning algorithm at the edge of a network. That was more of an experiment until we decided to move full steam with security as a key use case. And again, we are in 2013. There was almost no use of machine learning AI for security. And remember, pretty much everything was based on firewalls with static rules and signatures. So the idea was, can we use machine learning AI in order to detect some abnormal behavior that could be due to a zero-day attack? To that end, we started to design and develop some algorithm that could be used at the edge of a network, sitting on a switch or a router. The code was capable of studying the patterns and the traffic, cluster devices by similarity, and for each class of device, be able to develop and learn on-premise a model that would be used to detect some abnormal patterns. Then such abnormal issues would be reported to a central engine that would be capable of digging up and find out potential zero-day attacks. This has been, again, a fantastic use case and has been implemented in our products. This is in 2016 that we started to develop the first cloud at Cisco for ML/AI use cases, and I will just describe it in a few seconds, although there's so much to say about this architecture. But in a nutshell, the idea is to gather a very rich set of telemetry at the edge of a network. And you know that with a Wi-Fi controller, for example, you can have access to very rich telemetry data that could rely on gathering additional telemetry from the access point. And from the access point, you also have visibility on the end device as well. Then, upon collecting this data that would have been anonymized, of course, to preserve privacy, the telemetry would then be pushed to the cloud. And in the cloud, we started to build a very high-scale ML/AI cloud engine that is now used for many use cases, not just for Wi-Fi. This cloud would be capable of gathering a huge amount of data, make sure that the quality of the telemetry would reach some high standard, detect some missing data, corrupted data, and of course, we started to build very complex pipelines for machine learning algorithms to be trained. We came up also with many tools so that we can monitor the quality of the learning of the algorithm, of course, but of course at inference, detect some drift in the capability of the algorithm and things like that. So I would just like to pause for a few minutes, maybe, just to tell you more about the use cases for ML/AI in the context of Wi-Fi. We know that Wi-Fi is a fantastic technology, but tends to be fairly complex to troubleshoot. And again, at the time, everything was based on rules that were absolutely static. We did some very deep analysis of many networks, and we could see that for many variables, it was not possible to come up with static rules because it would be dependent of many more variables. For example, look at the throughput for a class of application. What would you define as a good throughput versus bad throughput? Well, of course, it depends of many parameters, such as the noise and the quality of the signal, the number of devices, the type and the nature of the application being used, and so on and so forth. The same applies to the time it takes to connect to the network, also sometimes known as the onboarding duration. It depends on how far you are from the authentication servers. It depends on many, many parameters. These are very absolutely perfect use case for machine learning because you do see from the beginning that you need to learn, and based on that you need to build a model. This is exactly what you see here. So in this example, we took the average onboarding duration, and an algorithm is used so that we can compute as a function of time and dozens of parameters for every single access point in the network. Then we can compute what you should expect for the average onboarding duration. And this is what you see as a green band. And of course, we monitor in real time. And when we are outside of the green band, which took years to be calibrated and make sure we have an amazing prediction algorithm, then when you step out, you go through a second layer that is then used to do root cause analysis. And this is what you see on the diagram at the bottom. We do root causing analysis, and then based on that, we can start identifying some issues. I just shown you one example. There are dozens of parameters and variables that are being taken into account to do modeling and then be able to predict multiple performance parameters of a network. It is absolutely automatic. There's nothing to do. And this is done for every single access point on the network. Then on top of that, you have the ability to rank how much you like, if you will, or I should say to provide a feedback on whether this is a good anomaly, this is a bad anomaly, and the system will adjust. This is what we sometimes call cognitive issue detection and analysis, and we did more than that. We started to look at long-term trends and provide you some insight when you have thousands of access points, and we monitor dozens of parameters and variables, and we can tell you when you start to see a slight deviation that is worth being looked at. We also provide some comparative analytics. This is yet another example of machine learning AI algorithm that can be used so that we can tell you how you compare from multiple performance metrics to other similar networks. And then in 2020, we started to look at endpoint analytics. And we all know that sometimes you see a device on the network, you just don't know what is the type of device and how you can do classification. What we used to do for years was, of course, to use rule-based, look at the OUI, look at the GHCP option and things like that to determine the type of device, but it may not be always available. So we started to define our own metrics, and then we would be using clustering algorithm so that we can regroup devices for which we don't know the type, and then you would just have to pick up one of the or two elements of a cluster, and then based on this label, we could grow a rule that could then be used by the system for better classification. And of course, the most immediate next step was to use machine learning for spoofing attack detection. So you have a new device that comes in, claims to be an iPhone, for example. What we do in this case is to use NetFlow records, and then we train multiple classifiers that will be capable of looking at NetFlow and then recognize the device type. So if a device claims to be of a given type, and we see in the behavior that it is not likely to be the device it is claiming to be, then we would put under quarantine as well. And we have a huge number of devices being monitored today, again, thanks to MLAI. Over the years, we came up with many tools so that we can look at the telemetry, and we all know that telemetry is extremely important. We could clean up the data, we can detect some issues in the telemetry quality, but also in terms of performance for the models. This is in 2019, and I really love this project because I faced a lot of skepticism, rightfully, by the way, when I realized that over the past 30 years of the internet, we've been using exclusively some reactive mechanism. In other words, you wait until you detect an issue. When you detect the issue, you start selecting a different path, which has been potentially pre-computed or recomputed on the fly, You can use a plethora of mechanisms at multiple layers, from the optical to MPLS to IP to BGP, but it is always reactive, and this is only limited to layer 3. So what we decided to do was to analyze millions of paths across the internet. If this is of interest to you, you will see in the description of this video some link to some analysis we've made of paths across the internet. The goal was to see if we could find some patterns that could be used in order to predict some issues before they happen. And the concept of predictive networks was born. And of course, at the time, the goal was not to predict every single issue, but guess what? In the internet, we're not making any prediction as of today. So what I wanted to do was to say, look, I may not be able to predict all issues. For that, I can react. But for the issues that I can predict, if I can come up with very high precision, then I may be able to close the loop and proactively reroute traffic before seeing the issue based on the prediction of this algorithm. But that was not enough. We wanted to be more ambitious, and we wanted to look not just at the path itself. And I'm sure you know the concept of brown issues or gray issues, gray failures, when basically the path is not completed down, but the quality is not sufficient, and because of that, you have SLA violation. So said differently, the goal of predictive networks is to model the network behavior, be able to predict some issues before they happen, the issues being capable of taking into account some SLA for the user, and then based on the prediction, potentially proactively reroute traffic before seeing the issue. And for that, as I said, we did some deep studies. You can find some white papers. Don't hesitate to look at another white paper about this kind of predictive technologies. And again, they are provided in the description. So in this case, what you would do for SD-WAN, as an example, the system would be totally automatic. It would use the telemetry from the analytics, which is a controller in charge of gathering the statistics for Viptela SD-WAN at Cisco. We have a lot of data related to the type of application being used, the volumetry, the BFD probes, and so on and so forth. And the system would start learning completely automatically without having to do anything. And it would tell you if the policy that is configured is not likely to be optimum in the coming days and weeks. And based on that, it could make a recommendation to switch to another policy based on the prediction. We looked at many technologies. I wouldn't have the time to talk about them now. We use our own homegrown applications to do that. The bottom line is that when we started to evaluate the efficacy of the system, taking 60 networks with almost 3,000 cities around the world, by looking at the number of users with SLA violation and without SLA violation, using the recommendation of a system, we could reduce roughly by 25% the number of users at maximum that would have SLA violation should you use the recommendation of such a system, which was absolutely an amazing outcome. And I was not even expecting to have such an accuracy on such a high percentage of issues. And then, we started to work on an amazing new concept. We ran this very deep experiment. Again, you can look at the white paper that goes into a lot of details about cognitive. Basically, the idea was, when you look at the past 30 years, how are we considering the issues of SLA? We've been very network-centric, if you will, by looking at delay loss and jitter, for example, coming up with hard values that should not be exceeded in order to understand the SLA for the user. And I believe that this is far from being optimum. And of course, it is way more subtle than that. So what we decided to do was basically to use machine learning algorithm to learn dynamically from feedback at the user level and taking into account cross-layer telemetry, what drives the QE, the quality of experience for the user. So we would go from an existing model today where you basically use a sort of magic equation using delay, loss, and jitter to compute a health score, or maybe not to exceed some hard-coded values, to a system that gathers some data from the user, and this is how we calibrated it, including a rich set of telemetry across the layer. So for the first time, you would get a model that tells you the probability for the user to be happy about a given application. Based on such a model, you can do some root causing, and if you can do some root causing, you may even be able to use this kind of feedback so that you can optimize the network for the QE. So you will no longer optimize the network for the average delay or bandwidth or you name it, but truly for the QE. We've shown that with such an experiment where we use feedback from 6,000 employees at Cisco with, again, millions of records of telemetry, we could see that it is indeed possible to learn dynamically what drives the QE for the user, and we can even use this kind of model across multiple applications. For the first time, we were capable of monitoring the QE for the user that has been dynamically learned for some applications, and we would be able to optimize the traffic in the network so that you can always optimize the QE for the first time. And I think this is really a breakthrough finding. And there are many things you can do, right? You can use QoS on the fly. You can basically route the traffic according to different paths. I won't say too much today about large language models and generative AI. This is the new chapter we started to open. We've been working very deeply into it, and I do believe this is going to lead to many new innovation in the future. But I'd rather stop now. I wanted to give you this overview of a 12-year journey. When we started, as you know, in 2012, nobody was really looking at MLAI for networking. We managed to show that it was possible to innovate at very fast pace with really, amazing breakthrough. And we have come up with many products deployed at scale, and there's way more to come. Thank you.